Yeah, so that's fine. So I'm going to record the screen. I've already started recording the screen. So anyway, let's see. I'm not sure what the quality will be like. Sometimes there's a little bit of a distortion introduced over there, but anyway, let's work with this for now. Yeah, thanks. Okay, so good afternoon, everyone. Sorry for the delay. So in the last class, we were talking about source coding, and in particular, in a previous class, we discussed variable length compression, and we saw that the optimal rate of compression for any random source is the entropy of the source, right? So the minimum compressed length is equal to the entropy of the sequence and entropy of the random sequence, or the entropy of the corresponding to the distribution. And we saw that it is possible to achieve that expected length. So it is possible to design a compression algorithm for which the expected compressed length is equal to the entropy, and this is a zero error variable length compression algorithm, right? But although it is possible, it is not it's not something that you can implement in practice, because it requires you to know the entire joint distribution Pxn, and for complicated distributions it also involves a very high computational complexity, because after all you have to sort all the sequences, all possible sequences, in the decreasing order of the probability, and then compute the corresponding compressed sequence, right? So therefore, although that algorithm is optimal, it is never ever used in practice, and people design better. And in fact, in the source coding course, which will be in segments 3-4, we'll see better compression algorithms which get you close to that performance. It of course doesn't achieve that performance, because after all that is the best algorithm, but then you can get pretty close to it, and that too very efficiently. So now we'll switch gears a little bit, and I'll talk about fixed length compression. So wherein we'll see that once again our discussion of fixed length compression will be brief, but we'll see that even here the entropy arises as a natural quantity. It arises as the fundamental limit of compression, even when we're talking about fixed length compression. So even if you talk about variable length compression with zero error, or fixed length compression with vanishing error probability, the optimal rate or the smallest rate to which you can compress a source sequence turns out to be the same, and it is equal to the entropy. And as we discuss fixed length compression, we'll see that there is a kind of a natural geometry. We'll get some more intuition as to why the entropy comes about as this term in the optimal rate of compression. Okay, and after that we'll talk about channel coding. We'll have a brief discussion about channel coding, where I'll introduce another term called the mutual information. And after that, we'll see the relationship between these various terms. We'll study the properties of entropy, mutual information, the relationship between the two, and so on. Okay. So any questions regarding what we've discussed so far? Okay. So now we'll talk about fixed length compression, where the goal is the following. We have a source sequence, or the raw file, which is an n length sequence consisting of n symbols, x1 to up to xn, and we want to compress this to a file or compress this to a binary sequence of length k, which we'll call ck. And the goal is to design this encoder and decoder, or compressor and decompressor, such that the reconstruction or the decompressed file is almost always equal to xn. We don't demand that xn hat should be equal to xn all the time. We're happy if almost all the time xn hat is equal to xn. So that is measured using the probability of error, which I'll call P subscript E, which is the probability that xn hat is not equal to xn. Okay, and now k is going to remain fixed. So k is going to be a function. K is a function of n. Obviously, if n increases, then k should also increase, and we'll also allow it to depend on the distribution Pxn. Okay, because if the distribution changes, then intuitively we do feel that k should change with Pxn, right? So k will depend on n and Pxn, but it does not depend on the actual realization of the raw file, right? So for different sequences of the same length and coming from the same distribution, k does not change. And we'll make another simplifying assumption. So we'll say that xn is now going to be an IID sequence according to some distribution Px. Okay, so each xi is distributed according to some known distribution Px. The rate of the compression scheme, as we've defined previously, is k over n. So the goal is to design the encoder and the decoder such that r is as small as possible, and also Pe is as small as possible. Okay, and we'll analyze this in the regime where n is very, very large. Okay, so we're interested when n is much, much larger than 1. In fact, we'll let n to tend to infinity. So the goal is to ensure that the limit as n tends to infinity k over n. So this is what we'll call r. So this is small, and we want that the probability of error also tends to 0 as n tends to infinity. Okay, it's okay if our compressor does badly for small n, for n equal to 5 or 10 or 20, the compressed length could be large, no problem. But then for a really large n, we want the compressor to work very, very well. And for many applications, that is really what we want. If you want to compress, you're not typically interested in compressing small files, right? Because then the gains that you would get in using compression would anyway be too small. So traditional compression algorithms focus on the regime where n is very, very large. You have an extremely large file, and you want to save space by compressing it to a much smaller file, right? So if you have, say, 100 kilobytes, going from 100 kilobytes to 1 kilobyte is okay, it's good, but that's not typically what you're interested in. But then if you have, let's say, a 1 gigabyte file and you can reduce it down to 100 megabytes, that makes a much bigger difference, right? So that's what we will be interested in. So as n tends to infinity, we want the rate to be as small as possible. That is k over n. The limit as n tends to infinity of k over n should be as small as possible. And for large n, we want the probability of error to also be vanishing. So for really large n, the probability of error should become smaller and smaller. Okay, so that is going to be our fixed length compression problem. And remember, we are focusing on the case where xn is IID according to some distribution Px. Okay, in fact, we'll make an even more simplifying assumption. We'll assume that xn is binary, and our goal is to compress binary sequences. Okay, we'll stick to Bernoulli sources. So the probability that x equal to 1 is equal to some p, and the probability that x is equal to 0 is 1 minus p. Okay, so each xn will be of the form, will be just some binary sequence. Right, and the goal is to compress this n length binary sequence into a k length binary sequence where hopefully n is smaller than k. Okay, so that's going to be our goal for today. Okay, any questions regarding the setup? Okay, so I'm going to state the solution, that is the optimal rate, even before I give you how we arrive at that particular solution. So the minimum rate of compression, at least for variable length codes, is, as we know, the optimal rate is equal to the entropy. Right? We've seen that in the previous class. And in this case, since we're looking at Bernoulli P sequences, we know that this is equal to P log 1 over P plus 1 minus P log 1 over 1 minus P. So by definition, this is the entropy. And if you're trying to construct variable length zero error codes, we know that this is the optimal rate of compression. We'll see that even if we want to do fixed length compression with vanishing probability of error, then this is still the optimal rate of compression. Okay, so if I try to plot the entropy, so note that this is completely parameterized in terms of P, and P, the probability of getting a 1, can vary between 0 and 1. So if I plot it out, this is what it is going to look like. Okay, so obviously if I look at the optimum rate as a function of P, so as a function of P, this is equal to this particular quantity, which I'll denote in the following form, H2 of P. Okay, so I'm introducing this subscript 2 to indicate that this is for a binary source, and it is completely parameterized by this quantity P. And this is what is sometimes called the binary entropy of P. Okay, this notation is my own, so sometimes different books or different papers use slightly different notation, but let us call H2 of P to be the binary entropy of P, and when I say binary entropy of P, I mean this particular function over here. Okay, so if P tends to 0, then this particular quantity also tends to 0, because 1 minus P log 1 by 1 minus P. So if you look at as P tends to 0, the first term P log 1 over P, this tends to 0, and 1 minus P log 1 over 1 minus P. So as P tends to 0, 1 minus P tends to 1. This also tends to 1. So log 1 is equal to 0. So this also tends to 0. Right? So as P tends to 0, the binary entropy of P also tends to 0. And as P tends to 1, well, the same thing happens, and H2 of P also tends to 0. Okay. Now, another point to note is that this function over here, it is symmetric in P and 1 minus P, right? So if P is equal to, whether you take H2 of 0 or H2 of 1, you get the same thing. And if you look at this plot over here, right, it is symmetric about P equal to half. Oops. Right, if you look around, it's a mirror image at P equal to half, right? and that can be easily seen from this particular expression, right? So basically P is the distance from 0, right? So this is the distance from 0, and 1 minus P is basically the distance from 1. Right? It is basically this distance from the right hand side, the distance from 1. So this would be P and this would be 1 minus P. So this distance is P, this distance is also P, this is P, and this is 1 minus P. So therefore the value of h of P is equal to the value of h2 of 1 minus P. This is h2 of P, this is h2 of 1 minus P, and both of them are the same. Right? So generally it is enough to just study the case when P is between 0 and 1, because 0 and half. So this is P equal to a half, because basically if you're interested in compressing sequences, binary sequences with P equal to let's say 0.4, then it is the same as compressing binaries or designing compressors for P equal to 0.6, because you can just interchange the zeros and ones. All right. So this is the optimum rate of compression, and our goal is to design compressors, fixed length compressors, for which the asymptotic rate, that is k over n for large enough n, is close to h of x, and the probability of error is really, really small. Okay, any questions? Yes. Okay. Correct. Yes. Correct. So that is why, so if you are getting a lot of information from that particular source, then intuitively it should be less compressible. If you are not getting much information, so let us say that I receive a binary sequence, okay, 1 0 1 0, something of this sort. Okay, so this or I observe some xn. I observe an n length sequence. If the n length sequence, if the probability of getting a 1 in that n length sequence is very, very small, is close to 0, then that source carries very little information. You know that with overwhelming probability, you'll see a very large number of zeros, there'll be a very small number of ones. So in some sense, it should be possible to compress that n length sequence into a much smaller length compressed sequence. Whereas on the other hand, if both zeros and ones are equally likely, then it should be somewhat harder to compress, right? Because you don't know, you can't really predict what the next symbol of the sequence is, so therefore it should be more harder to compress. Whereas if you can very easily predict what is going to happen, then it should be easier to compress, and therefore the compressed length should be smaller, and therefore and intuitively you're getting less information, because it is easier to predict. The more easier it is to predict, the less information you're getting by observing the outcome, and the harder it is to predict, the more information you're getting after observing the outcome. All right. Okay. So now, what is our goal? The goal is to construct these encoders and decoders such that, well, k over n, so this tends to something close to the entropy as n tends to infinity. Second, the probability of error, which is the probability that xn is not xn hat is not equal to xn, this tends to 0 as n tends to infinity. Okay, so this is our goal. Now again, I will not give a full proof, a formal proof of how we are going to construct it. I'm going to tell you how we might construct such a compression scheme, but then we won't do all the steps. Okay, you'll find some more details in the lecture notes which I have posted on the course website, but that is the exact calculations are not important. The intuition is perhaps something which is very important. Okay, so the basic idea is the following, right? So let's think about what an optimal, what does a fixed length compressor do? Structure of, in fact, any fixed length compressor. Remember that the only way we are measuring the performance of any compressor is using these two parameters, k or k over n, and the probability of error. Okay, we don't really care how exactly the compressor is constructed. There could be different ways of constructing compression schemes with the same k over n and the same probability of error, but that doesn't matter. All of them are equivalent to us. Okay, yes. Correct. 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 So that's the point. That's the beauty of it. So it's possible to have k much smaller than n. So okay, so let us take a simple example. Okay, let us assume that our sequence xn, okay, the sequence xn, this is, say, Bernoulli. It's an IID sequence, IID Bernoulli, let's say 0.1. Okay, so what is h of x in this case? So 0.1, which will mean that this is somewhere around 0.4 or so. So h2 of p or h of x is something around 0.4. Let's say it is 0.45 for convenience. Okay, so h2 of 0.1 is, let's say, 0.45. Okay, so what this is saying is that for large enough n, the n length sequence can be mapped into a 0.45 n length sequence. So you're basically removing more than half the number of bits. So the reduction in the number of bits is more than a half, but even then the probability that xn hat, and there is some way of reconstructing, so I remove half the bits and then I have some way of reconstructing it to get back another n length sequence, such that the original sequence and this reconstructed sequence are equal almost all the time. Okay, so I have an n length sequence xn, correct? So I'm doing some complicated function. So from this n length sequence, I'm going to get a 0.45 n length sequence. 0.45 because 0.45 is the entropy corresponding to 0.1. Right? So I'm getting so I'm taking an n length binary sequence. I'm converting it into a 0.45 n length binary sequence. So for example, I take 1,000 length sequence. I'm converting it into a sequence of length 450, right? And I have some way of getting back another 1,000 length sequence such that these two are equal, this and this are equal almost all the time, right? The probability of this not being equal to this is very, very tiny. Okay, so in some sense it means that it doesn't mean that half of the bits of this are removed. It means that there is some way of converting it into a sequence of length 450. Okay, or the effective information that is contained in every bit is roughly 0.45. The difference between n and k is more, but again the claim is that you're not losing a lot of information in going from here to here, right? Because you can reconstruct xn with, so x is a probability of x hat not being equal to x. This is very, very tiny. This is maybe less than or equal to let's say 10 to the minus 4, say. Well, it's maybe not 10 to the minus 4, but let's say 10 to the minus 2. Correct. Map it back. Correct. So obviously not every sequence can be mapped, but it turns out that the only sequences that you need to recover are those which occur with high probability, right? We're still, remember, we are tolerating a small probability of error. It's okay if the probability of error is small. I'm not saying that the probability of error is equal to 0. As n tends to infinity, it becomes smaller and smaller. Maybe as n goes from 1,000 to 10,000, this goes from 10 to the minus 2 to 10 to the minus 3, 10 to the minus 4. So you fix something, say 10 to the minus 6, okay, and you choose an n which is very, very large. Maybe the n that you're choosing is something like 10 to the 7 or so. It's actually very, very large, not reasonable in most cases, but at least in principle. So you take a very large block length, or you take a very large size of the raw file, and then you want to ensure that the file can be reconstructed with probability of error 10 to the minus 6. Okay, and the claim is that this is possible even if k is much, much smaller than n. Okay, n is very large. Not for small. Correct. Exactly. Yes. So if p is very small or p is very large, then it is then the gains that you get is even more. Right? K can be made much smaller than n. So okay, take an extreme case. Okay, take an extreme case. Okay, p equal to 0. Okay, let's assume that both the encoder and the decoder know p. Okay, this is given to us, and both of them know n. Take any n, doesn't matter. It could be 10, it could be 10,000, it could be 100,000, no problem. So now, how many bits do you think you need in order to represent the source sequence? Remember, your goal is that the probability of error is small. Let's say 10 to the minus 5. In fact, you can make it the probability of error equal to 0 in this case. So what does p equal to 0 mean? Exactly. Do you even need 1 bit? Correct. So not even 1 bit is required, because if, again, the assumption here is that both the encoder and the decoder know p and you know n. Correct. So then what you can do is the encoder sends nothing at all. The decoder, he knows p, he knows n. So all he has to do is output a sequence of all zeros of length n. Correct. So k is equal to 0 in this case. K equal to 0 for any n, and the probability, and this is going to be certain, right? You know that p is equal to 0, and therefore you don't need to send any bits at all. The same holds when p equal to 1. Right? You know that it is always going to be a sequence of all ones. So even in this case, k equal to 0. Correct? So now if you sort of try to extrapolate this, if p is very, very, very small, okay, if p is very tiny, then you can imagine that you don't need so many bits. Right? So for example, one sort of very simple way to do it is that let us assume that we're only interested in compressing sequences with exactly one. Okay, you have an n length sequence xn, both the encoder and decoder know that the number of ones is equal to 1. Again, the model is now slightly different from what we have, but again, this sort of illustrates the point. Let's assume that the encoder and the decoder know that the number of ones, there is exactly one in the entire sequence, and you want to compress the sequence. So maybe n is equal to 100,000. Okay. So how would you design a compressor? What information do you actually need to convey? Okay, length is available for free, right? So both the encoder and decoder know n, and they know that the number of ones is exactly equal to 1. So in some sense, this is the distribution, right? This is the joint distribution, and you know exactly what n is. Correct. So if let's say you had to design a compressor, what would you do? Exactly. So all you need to do is convey the location of that particular one, right? You know that there is exactly one. So therefore, all you need to do is convey the position of the one. So the encoder simply outputs the location of the one. Correct? So how many bits do you need to represent the location? You know that the sequence is length 1000. Correct. Correct. So you can have k to be equal to ceil of log to base 2 of 100,000, right? Which is ceil of log n to base 2, which is much smaller than n, right? So this is a way you are getting compression, even though you're taking an n length sequence, you have some information about that sequence, right? You know the statistics of the source, and you're using that property for which to compress it from n length sequence to a log n length sequence. Okay, so in this case, the encoder and the decoder know that the number of ones is exactly equal to 1, correct? So now let's again try to extend this a little bit. Let us assume that this property holds, that the number of ones is equal to 1 with very, very high probability. Okay, the probability that the number of ones is greater than 1 is maybe less than, maybe the probability that the number of ones in xn is greater than 1, maybe this is less than or equal to 10 to the minus 3 or something like that. Okay, all right, or maybe again hypothetically, let us assume that this is less than or equal to 1 over n. Assume it's a weird source, doesn't matter, but let's assume that the joint distribution has this property. And our goal is to, and remember, our goal is to construct a fixed length compressor for which the probability of error is vanishing in n and the rate is as small as possible, right? K is as small as possible. Now you can use the same approach, right? You can say that you can just use log n symbols, take K equal to C log n. So the rate is just K over n equal to log n over n. And the probability of error, so you make an error if the number of ones is strictly larger than 1, right? It is exactly this particular thing, because if the number of ones is exactly equal to 1, then you're anyway sending the location of that particular one, so you'll be able to reconstruct it correctly. But if the number of ones is greater than 1, then you don't care. The encoder doesn't care what it's sending. It sends some garbage. The decoder will output some garbage, doesn't matter. But the probability that that is going to happen is small, right? So this is less than or equal to 1 over n, which tends to 0 as n tends to infinity, right? So therefore you have a scheme with vanishing error probability. The rate is small. It is much smaller than n. In fact, what happens to this as n tends to infinity? What is log n? What does log n over n tend to as n tends to infinity? Yes, so it tends to 0, right? So log n over n tends to 0 as n tends to infinity. So for asymptotically large n, you are achieving vanishing error probability. The rate is also vanishing in n, right? So this is ultimate compression. But again, you have to note, you have to keep in mind certain things. One is that we have this very special distribution which is known to both the encoder and the decoder, and the second it is that you're allowing a certain probability of error, right? You mean here? You mean here? This one? Yes. Yes. Okay. So again, so you have to think about the way we are sort of modeling this problem. So we're assuming, again, we're assuming that P is known and N is known, correct? So our assumptions, so let us go back to so the question is where P equal to 0, the claim is that K equal to 0, the probability of error is also equal to 0, correct? But the assumptions we have made, is that N and P are known. Okay, and how is this known in practice? It's of course not known. There's no genie which is telling you what N and P are. But the way you typically realize this is in practice is using a header. So the compressed file, generally for most practical compressors consists of two parts. One is a header which contains all of this information. It contains information about n, it contains information about px and so on. And the remaining is the actual compressed sequence. So this is the ck. Okay. So one way to think about this particular case is that of course there will be a header. So this header will contain information about n and px, but then k is equal to 0, which means that nothing else needs to be stored. So this is a sequence of length k. So as we are studying the problem of compression, we are interested in minimizing this part. This is an additional overhead which will always be present because you need to convey some amount of information. Now, if you want to really do ultimate optimization, you should also you should also make sure that or you should try to design the header, try to make it as small as possible and so on. But we'll assume that this is some extra overhead which is kind of available for free. And in any case, this does not, if n is very, very large, then the header will anyway be much smaller than what is required for k. But what you also always have to keep in mind is that this header will always be present. So the overall compressed file will have these two parts. And whenever I'm saying that k is very small, what I'm saying is that this part of the compressed sequence is very, very small. Okay. So that is why we can say that k equal to 0, which means that the compressed file will only contain the header and nothing else. Does that make sense? Yes. Mm-hmm. Correct. Yes. Correct. That's a very good observation. In fact, that is true. For very small n, the header itself will occupy a huge amount of space. And that is what you will notice if you try to compress a very small file using zip. So if you try to if you try to zip maybe a file which has maybe 10 bytes or 5 bytes, you'll see that the compressed file is actually even larger. It will be much larger than 5 bytes or 10 bytes. And that is precisely because you have this header information which is going to take at least a certain amount of space. And therefore compression is not useful if you have a very small file to compress. So most traditional compression algorithms work well when the size of the file, when n is very, very large. And that is really the regime where we can ignore the effects of the header. So the header will be small because this is typically logarithmic in n. So this header size is typically going to be logarithmic in n, and as we've just seen, log n by n tends to 0 as n tends to infinity, so we can ignore all of these effects. We can assume that n and px are known both to the encoder and the decoder and so on. So that is why we're making this assumption that this is given to the encoder and the decoder, but whereas in practice this needs to be stored as a header, and this can be ignored only when k is very, very large or n is very, very large. Any questions? Yes. Mm-hmm. Yes. Mm-hmm. Mm-hmm. Correct. Yes. Okay, so again, you have to be a little careful with that. So, so the assumption is that you're measuring in terms of bits, right? Of course, the way you implemented it was kind of very simplistic, but let us assume that you had what, A, B, C, D, and E. Let us assume that A is represented using 0, maybe this using 1, 0, 1, 0, 1, 1, 0, sorry, yeah, whatever, maybe 1, 1, 0, 1, 1, 0, 0, and 1, 1, 1, 0. Okay, so let's assume that this is the mapping that we're using. Okay, for simplicity. Now, now of course, if you didn't do any compression, or sort of the naive way of storing this would be using fixed length binary, right? So you would need ceil of log 5 to base 2, which would mean that so this would be equal to 3 bits. So if you knew that your universe consisted only of A, B, C, D, and E, if this is your alphabet, then you will, without, if you didn't do any sort of compression, then you would represent this as each A as a sequence of 3 bits, B as a sequence of 3 bits, and so on, right? But now, by employing this variable length scheme, now certain characters are going to take more than 3 bits, but some characters are going to take much less than 3 bits, and that is how you get sort of compression. Yes. Exactly, ASCII value. Correct. Yeah, exactly. So if you just stored it in, so basically when I'm saying in its raw form, think about it as an ASCII character. But then now ASCII, now using ASCII, if you use 8-bit ASCII, then you have 2 to the 8 possible values, right? But then if you look at typical English text, you don't see 2 to the 8 different characters. It's typically the English alphabet along with punctuation marks and maybe certain special characters. That's it. So you're using far fewer than 2 to the 8 possible characters, and some of those characters occur much more frequently than others. For example, vowels occur very frequently, spaces occur very frequently, and so on. And you can use all of that to design these variable length compression algorithms. Right? So think of this as something similar to Morse code, right? So if you heard of Morse code, you basically represent characters using dots and dashes, and the number of dots and dashes. So typically one dash corresponds to 2 dots. The length of the dash is or the interval of a dash is twice the interval of a dot, and therefore the most frequently used letters have small Morse codes, and those which occur very less frequently, maybe characters such as Q or Z have a much longer representation, whereas characters such as E or A have very small representations. Okay, so maybe that's the way to think about these variable length codes. Okay. All right. So now that we've got some intuition. So remember, let's try to build up on this particular scheme. Okay. So number of ones is greater than 1. Okay. Now we know that xn is IID Bernoulli P, right? So how many ones do you expect to see in this? Number of ones is roughly going to be equal to n times p, correct? So therefore, and in fact the probability, we made this more formal, the probability that the number of ones in xn the probability that this minus n times p, so the probability that this is greater than some n times epsilon, this tends to 0 as n tends to infinity, or the probability that the fraction of ones in xn, so the probability that this deviates from p by an amount greater than epsilon, we know that this tends to 0 as n tends to infinity. This just follows from the weak law of large numbers, or you can get a better bound on this using whatever, Chebyshev's inequality or Chernoff bound, right? So this follows from the weak law of large numbers. So if you know that the sequence is Bernoulli P, then you know that with overwhelming probability, the number of ones in xn will be close to np, okay, or the fraction of ones is going to be close to p. So why not use this to design a compressor itself? So in some sense, these are the useful sequences. Okay, these sequences are what we want to reconstruct exactly. If the number of or the fraction of ones is much larger than np, then you don't care if that corresponds to an error or not. Okay, so I'll define this set S as the set of all binary sequences. So it is a set of all binary sequences such that the number of ones in xn, or I think I had used a notation to define this. So mu1 of xn, the number of ones in xn, is less than or equal to np times 1 plus epsilon, but it is also greater than or equal to np times 1 minus epsilon. Okay, so you look at only those sequences for which the number of ones in the sequence is close to n times p. Okay, so this is going to be some set. So it's going to be a set which is a function of epsilon, it's a function of p, and it's a function of n. Correct? So these are the sequences that are important to me. If the realization of xn is not in this set, then I don't care if there's an error. So I want to reconstruct these sequences exactly, and other sequences I don't care. So we know that the probability that xn lies in this set S, this is very large. So this tends to 1 as n tends to infinity. So the question is, how many sequences are there in this set, right? So maybe I list all possible sequences in this particular set. So list all sequences xn of 1 up to xn of size of S. There are a certain number of sequences, and for each of these I will assign a code word of the same length. So 0 of a k length code 1, and so on, all the way up to 1, 1, 1. So how many bits do I need to represent a sequence in this set? Yes, anyone? Exactly. So it is a seal of log, so log size of S to base 2. Correct? So these are the number of bits needed to represent any sequence in S. Assuming that, of course, you know S both at the encoder and the decoder, which is anyway known because this epsilon is decided beforehand. P is known both to the encoder and decoder. N is known both to the encoder and decoder. So you need these many bits, and the claim is that as n tends to infinity, this is going to be very close to n times h of x, or n times h2 of p. All right. So we'll maybe continue this in the next class. And again, you have seen most of this going from here to here in your assignment itself, because all that remains is to count the number of sequences in this particular set. You know that the number of ones is roughly close to NP, so you can compute it exactly, and then you can obtain a bound on the number of sequences in this particular set, and that turns out to be, the size of S turns out to be approximately 2 raised to n times H2 of P, which is much smaller than 2 to the n, which is the total number of sequences. All right, any questions? Yes. H2P. Yes. Yeah. So for example, if H2 of P is 0.1, right, then this is 2 raised to 0.1 n, but 2 power n is the total number of binary sequences of length n, right? So in effect, you're discarding a lot of the sequences, or many of the n length sequences. In fact, you're discarding 2 to the n minus 2 to the n H2P is number of sequences. You're only keeping 2 to the n H2 of P sequences, that is those which lie in this set, and these are going to be assigned valid code words. The sequences which are not in this set, it doesn't matter what happens to those. So these are sort of the important sequences, and you know that the probability that you'll observe a sequence from this is very large. It can occur, right? It definitely does occur, but the probability of occurrence of some sequence which does not lie in this set is very tiny, and as n tends to infinity, right? Those will be mapped. So maybe you can map all of them, all sequences which are not in this, to maybe the all zero sequence. Okay, so basically the encoder will look like this. So you have X. Sorry, I didn't hear that last word. Can you please repeat? Yes, small. Yes, exactly. So the actual encoder will look as follows. You list all possible sequences in S, and then now there are many sequences which are not in S, right? So these are not in S all the way up to xn of 2 to the n. Now all of these are going to be mapped to one of these. Doesn't matter. This is what the encoder will do. Maybe everything gets mapped to this, all one sequence, right? And the decoder will observe this, but it is going to output xn of 1, xn of 2, up to xn of size of S. So if any of these sequences actually occurred, then that will not be reconstructed correctly. If any sequence from here occurs, then it will be reconstructed correctly. So the probability of error is therefore the probability of occurrence of any one of these sequences, and we know that the probability of occurrence of a sequence outside the set S is vanishingly small. Okay. Any other questions? Okay, so if not, when we meet next week, see you then.